Today we're going to see how to implement and train some simple neural networks. In this first lecture I will cover some basic concepts, so a bit more abstract yet, doing some basic revisions of algebra, particularly matrix multiplication, which will be very important for implementing the artificial neural networks. And then we're going to see how TensorFlow can help us train the network by computing the derivatives that we need for backpropagation. So you're going to see these notions of computational graph that TensorFlow builds and automatic differentiation. And then I'm going to talk a bit about some more practical aspects of training the network with stochastic gradient descent. And after the break in the second lecture, we'll dive into TensorFlow and I'll show you how to actually write the code and implement these. So let's start with revising some basic algebra concepts. We're going to be talking a lot about tensors, but we can distinguish these objects, the scalar, which is just a simple number, the vector, which will be an ordered array of numbers in one dimension, a matrix, which is the kind of objects that you learned how to use in algebra, so basically a two-dimensional array of numbers, which has a specific algebra that we're going to use. And then a tensor formally is any relation between sets of these kinds of objects, but for our purposes here, we'll be referring as tensors any n-dimensional array of numbers. And this is basically what we are using in TensorFlow. We are using tensors to store our data, and then the tensors are passed over between operations in the computation graph, and that's why where the name TensorFlow comes from. So one thing that we can do, and you probably already did with NumPy, with arrays and matrices and n-dimensional arrays, is to do this sort of operations, adding and subtracting element by element. So even in algebra, using matrices and vectors, we do this. So if we have these matrices of the same size, we can add or subtract them simply by applying the operation for the corresponding elements. So the first one with the first one, the second one with the second one, and so on. This is something that you can do with tensors in TensorFlow. So the broadcasting rules are more general than these algebra rules, and the same broadcasting rules that we can use in NumPy, we can also use in TensorFlow. But one important algebra operation with matrices is this matrix multiplication. So if you follow the algebra rules, when you are multiplying matrix A by matrix B, you are not doing that element by element, but you are doing this operation. So for matrix A, the first one in the multiplication, we need to have as many rows as the columns we need to have, we are going to multiply each column of matrix A by each row of matrix B. So for each column of matrix A, we need to have one row on matrix B. That is the requirement so that we can do this operation. And now each cell of the resulting matrix, here matrix C, will be the sum of these products. So the first element of the first row of matrix A multiplied by the first element of the first column of matrix B, and then the second with the second, and so on. And then we add all of these products and we obtain the first cell of matrix C. And we do this for all the combinations of rows and columns on the two matrices. So the requirement is that the number of elements on each row on matrix A is the same as the number of elements on each column of matrix B. And then the size of this matrix will have the same number of rows as we have for matrix A, and we'll have the same number of columns as there are in matrix B. So the reason why this is important for neural networks is that if you look at how we are going to model the neuron, we have this first step where we compute the product of each feature in the input vector with the corresponding weight on the neuron, and then we add all of these products to get this value that we're going to pass to the activation function. There is still a bias value here. We're going to talk about that later, but basically this first step that we are doing here has exactly this structure, this procedure. So if you imagine that we have in matrix A a set of examples, for example, a mini batch that we're going to use to train our network, and each example is corresponds to a row where each feature corresponds to a column. So this would be example number 1 and all the different features, example number 2, and so on. And if we model the neurons on this layer in columns, so this would be neuron 1 with all the weights of neuron 1, all the weights of neuron 2, and so on. Each neuron is a column. By doing this matrix multiplication, we obtain in this matrix here the corresponding values that we need for the activation function for all the neurons that we have in the layer. So each neuron will be contributing one column in this matrix here, and each example will be contributing one row in the matrix that is the product. And you can see this as a new set of features for all our examples. So if you have 10 examples here, we will have 10 rows here. If we have 5 neurons, we will have 5 columns, and each neuron will be giving one new feature for our data, and all the data that we input will be represented here in the same number of rows. So basically this is doing that kind of transformation where we input our data and our network starts transforming all the features into new features. We need to do a nonlinear transformation, but that is done by applying the activation function on this matrix and then obtaining all the activation values for all the neurons in columns and for all the examples in rows. So this matrix multiplication will be at the core of neural networks when we are computing all the activations, and then of course also when we are training, because this is one necessary step for training the network. So another thing that you can do in TensorFlow with tensors is broadcasting, like NumPy. For example, you can do operations between one matrix with n dimensions and another tensor with fewer dimensions. If they have the same number of dimensions, the dimensions must match. Otherwise, the TensorFlow will follow the same broadcasting rules of NumPy. It will align starting from the last dimension. So in this case, it will align the elements of these vectors with the columns of this matrix and then broadcast through the remaining dimensions, through the rows. By combining these kinds of operations, we can do batches of operations over larger dimensional tensors that represent, for example, sets of matrices and so on. One useful function in TensorFlow is this matrix multiplication, matmul, that applies this algebra multiplication between two matrices, but it only does this multiplication on the last two dimensions of the tensor that we provide. On the remaining dimensions, it will broadcast this operation. So, for example, we can have a three-dimensional tensor with this shape, where we have two layers of 2 rows and 3 columns. We can imagine this. So this is a matrix of 2 rows by 3 columns, but we have 2 of them stacked. And this here we have a matrix of 3 rows by 2 columns, and we have 2 of them stacked. And if we use matmul, it will apply matrix multiplication on these last 2 dimensions, but it will broadcast over the whole stacks. So we actually get automatically 2 matrices in this shape, so resulting from the matrix multiplication of these last dimensions. But we get 2 of them because we have 2 on this tensor and 2 on this tensor, and so the first one is multiplied with the first one and the second with the second. This allows us to do lots of these operations in one go, in one instruction, and it allows TensorFlow to optimize all of these computations as best as possible. And TensorFlow can automatically send some of these computations to GPU, others to CPU, and so on. So this will be at the core of what we're going to do when implementing things in basic TensorFlow. It's important to note that in practice, we will not be looking at this very much. So when we start using the Keras interface, we will no longer worry about the details of the algebra at this lower level, except if you need to do some tweaking or if you need to adapt something at this level. But in general, we're just going to use the layers that Keras provides, fit them together, and don't worry about the details of these operations. However, it's important to understand how this works, not only if you need to look at this lower level, but also because even when working with Keras, you need to make sure that the shapes of your tensors fit together appropriately. So you need to understand what kinds of operations are being done to be able to think about it and to design the architectures of your networks without making mistakes. So all these models will be based on these types of operations. Typically, we're going to use tensors as the input to our network that represent batches of examples. So if all your examples are vectors with features, then the tensors will be two-dimensional because you'll have a batch of examples. If your examples are more complex, you can have examples that are images, grayscale images. In that case, you'll have a three-dimensional input. If you have color images where each example needs to have red, green, and blue, then you'll have a four-dimensional input into your network when you put in a set of examples. So the input can be of higher dimension, but in any case, you need to understand what TensorFlow will do with those tensors and how the tensors must fit together with the appropriate shapes. So then we're going to use these kinds of operations to activate the network, and then our loss functions will aggregate all of these values, for example, measuring the error based on the last activations and so on, and that fitting everything together will be the neural network. So let's start with a basic example. Let's suppose we want to classify these data, so separate these two classes, red and blue, and we're going to use a very simplified neuron, which is not even a basic neuron. It just has two weights and then the activation function, and the weights are multiplied by the two features of our point. So the features are the coordinates, the x and y coordinates here on this plot. So let's call it x1 and x2. These are the features that determine the position of each point. We have two weights, each one multiplied by one of the feature, one activation function, and then we use the sigmoid activation to tell us whether this should be red or blue. So if it's close to 1, we say it's red. If it's close to 0, we say it's blue. We can model this by using a matrix for the batch of values that we want to present to our network. And then we can represent the weights of our pseudoneurons as a matrix with a single column. So when we do matrix multiplication, we obtain a matrix that has as many rows as the number of examples we presented to our neuron. It will have only one column, which corresponds to this net value for our neuron. And the result here is given by the matrix multiplication rule, where we multiply the first feature of the first element by the first weight, which is this product here, and then we sum the second feature multiplied by the second weight, and we get the total here on the first row. And we do this for all the examples. So with matrix multiplication, we can obtain these values for all the examples in the mini batch we are presenting to our network. Then we need to apply the sigmoid function. So if we apply the sigmoid function to this matrix here, since the TensorFlow will do the broadcasting with this function too, it will return a matrix with the same number of values, but after applying that sigmoid activation function. So this way we get the activations for all the batch of examples that we presented the network. Okay, so now we're going to use that for training, and we're going to use backpropagation, as we saw before, to find the gradient of the loss function with respect to each of the weights we need to adjust. So the basic idea of backpropagation is to chain all the derivatives of the basic operations in order to reach the weight we want to adjust. So in this case, we have a loss function, an error function. So we need to compute the derivative of the error function with respect to the output of our network, then the output of the network, which is the output of the activation function, with respect to that weighted sum of all the inputs that we feed into the activation function, and then the derivative of that weighted sum with respect to the weight of the neuron that we want to adjust. And this is for a single neuron or the output neuron. If we have a deeper network, then we have to keep chaining this over all the layers, adding the contributions to all the neurons from all the neurons that are forward and so on, and do this to compute how much we need to change each parameter, each weight, in order to reduce the value of the loss function. So backpropagation is a special case of what is called reverse mode automatic differentiation. We're going to look a bit more at this, but basically the idea here is that if we know all of these derivatives of the elementary operations, we can chain them all together, going backwards from the end, the loss function, to the beginning, so each parameter that we need to adjust, and this way compute the gradient of the loss function for each of these parameters. So there are several ways we can do this for computing the derivatives. One way we've been doing so far, when I've talked about backpropagation, is to manually do the symbolic differentiation. So we compute what are the derivatives of all of these after we obtain the expression for the chained derivatives. For example, we saw that the update rule for one weight of the last neuron in the network would be minus this learning rate multiplied by the derivative of the error function with respect to that weight. And analytically, if we consider a quadratic loss function and a sigmoid activation, we calculated the expression for all of these chains of derivatives. Now, this is not a good approach because we can do this easily for a very simple network, but when things start complicating, and if we have networks with different activation functions and various architectures and lots of neurons and so on, doing this by hand becomes increasingly difficult, and it will not be at all practical for deep learning. So if we have very large networks, we would spend a huge amount of time trying to get all the expressions for all the derivatives of all the parameters in the network that can be hundreds of millions easily. So another approach that does not require this symbolic computation of the derivative expressions is to use numerical differentiation. Numerical differentiation takes small finite steps to compute the differences between the values of the functions when we change slightly the input values. So if we want to compute the derivative with respect to some weight, we could see how much the loss function would change if we change the weight by a very small amount and then use that difference as an estimate of the derivative. Now, this has the advantage that we do not need the analytical expressions, but it's extremely inefficient. And you can imagine that if we need to do this for all the weights on the network for every step in training, then training would take a huge amount of time and huge computational requirements. So numerical differentiation would not be feasible for training deep neural networks. In addition, there is also the problem of convergence, because if the functions are steep, have very large oscillations, then it can be very hard to do numerical differentiation accurately and converge to the right values. So what we do here in TensorFlow is called automatic differentiation. Basically, we just need to know the analytic expressions for all the elementary operations that we're going to apply. So we need to know the analytic expression of the derivative for the error function, for the activation functions, for these weighted sums, and so on. And if we know for each of them what is the derivative, then it is possible to chain these derivatives together when we are doing these operations. So this is the idea behind automatic differentiation. We are basically applying these chain rules to all the elementary operations, using their derivatives along with the computation of the actual values of those operations. So this can be applied in general to any architecture that you have, any combination of activation functions and layers and so on, as long as we know the expression for the derivative of each basic operation. So we need to have basic operations that can be differentiated, and we know how to compute those derivatives. So in TensorFlow, this automatic differentiation is implemented in this manner, called reverse mode automatic differentiation, which is the same idea that we saw in backpropagation. We start at the end, and then we chain all the derivatives going back to where to those variables that we want to compute the derivative with respect to. So basically, we have a first forward pass where all the operations are applied, so the network is activated and the intermediate results of those operations are kept. We know all the activations. And then we have a backwards pass where all the expressions for the derivatives are applied, going backwards from the end to each of the variables, each of the parameters that we want to differentiate with respect to. So this will go through the computation graph, and this computation graph is, you can imagine a graph where the nodes are all these operations and the edges are the tensors that transfer the data between different operations. So we're going to see in the tutorial today a simpler example of automatic differentiation, which uses forward mode automatic differentiation. In this case, we use dual numbers to keep track of both the function and derivative values along all the operations, and we accumulate both the values and the derivatives as we apply all these functions. The reason for showing you forward mode automatic differentiation is that we want to give you an idea of what automatic differentiation is, in particular to distinguish from numerical differentiation, so that you understand that this is not at all the same thing. However, reverse mode automatic differentiation is a lot more difficult to illustrate with an implementation, and since the details here fall outside the scope of the course, this is just to help you understand the difference and not for you to memorize all the details. We have a simple tutorial showing you forward mode automatic differentiation, just to give you the idea of this process. But let's see at a higher level, so without looking at the implementation details, how this is done in TensorFlow. So let's suppose that we want to perform this very simple operation here. Find the value x that minimizes the function cosine of x. So if we want to minimize this function, we need to compute the gradient, and we need to slide down the gradient so that we find the x at the bottom of the values of this function. So when we give this to TensorFlow, this operation, cosine of x, TensorFlow will create as part of the computation graph. So here we have our input, x, cosine of x, and then the output. This is the basic graph that we created. But TensorFlow will also add information on the gradients. And the derivative of cosine of x is minus sine of x. So added here to the graph will be this set of operations where we have the sign function and the multiplication by the negative there, so that we also have the gradient of the cosine expressed in this manner. Note that this is the actual analytic expression for the gradient, so this is not a numerical approximation. This is the derivative of cosine of x, but TensorFlow will add that to the computation graph, so that when we want to compute the derivatives to do the minimization, it will use this part of the graph to have that to compute those derivatives. And this can be more complex. For example, we want to minimize x squared multiplied by cosine of x plus sine of x. So aside from creating the computational graph for this computation, TensorFlow will also include the gradient information, where we have the cosine of the gradient, the cosine of the square, the multiplication of the two, and so on. So it will chain together all the corresponding derivatives of these operations, so that we have a computation graph in parallel with the one that computes the output of our operations. We have a computational graph that can be used to compute the derivative with respect to the variable that we're using there. So this will be a basic element of using TensorFlow to train our networks. TensorFlow will automatically create these graphs, because to each operation that we use in TensorFlow, it has associated all the information for computing the derivative. And every time we chain together these, or we compose these operations in our expressions, TensorFlow will keep track of that and create the corresponding graph for the derivatives too. So now we can use stochastic gradient descent to train this very simple model. We can use the information on the gradient to adjust the parameters in our model. So since we can compute the derivatives, we can now slide down the loss function. So here I'm representing in this graph the two parameters that we have, the two weights of the pseudo neuron we have here as the two axes in the plot, and the depth, so the z-axis, is the loss function. We have a peak here where we have lots of errors, and then as we go down we start reducing the number of errors until we find the best combination of parameters here for minimizing the classification errors on these data. So this basically we are doing with stochastic gradient descent, because since we can compute the derivatives with respect to the parameters, we present some examples, estimate the derivative, and slide down that gradient. So it's gradient descent because of this motion here. We're sliding down the gradient of the loss function. And it's stochastic because at each update to our weights, we are presenting a random mini batch of examples. So this sliding down here I'm representing 1 point per epoch, so after passing through all the data, but each update is done using a small sample of the data that we have. And this gives some randomness to the trajectory here, because since we are not computing the actual gradient of the loss function, because that would require using all the data, we are estimating the gradient at each point from a random sample of the data. So this is the basic stochastic gradient descent, where we estimate the gradient at step t by looking at the average of the loss function over a sample of examples. So just to explain here, we have this loss function that depends on the output of our network, and the output of the network depends on the input that we give it, each example, and the parameters that we currently have. So although in this case, in our simple network, we have these two weights, so depending on the values of the weights, the output of the network will be different. But we are also comparing that with the desired output, because we know we have the labels for all the points, so we know what the classification should be, and we compute here the loss function. For example, the logistic loss function or the quadratic error, something like that. What we are doing for stochastic gradient descent is estimating the gradient of the loss function for all the data by just using a sample of m points. So we're going to compute this loss function for each of these m points, and then we're going to have a gradient that is the average over all of this sample. And with stochastic gradient descent, simple stochastic gradient descent, we're going to use this value, this gradient here, multiply it by a small number, the training rate, and then subtract that from the parameters that we have at time t in order to obtain the parameters on the next step. So this subtraction is because we want to go down the gradient. If we added this, we would go up the gradient and we would increase the loss function. That's not what we want. So this is basic stochastic gradient descent. It's stochastic because since this is a random sample, we are not actually getting the exact value of the gradient. We are getting an estimate based on that random sample. But this can be improved with momentum. Momentum takes advantage of the fact that often we are going down, we are sliding down always in the same direction. So instead of slowly rowing down the hill here always in the same direction, which is what happens when we just use the gradient as the value to update, we can use the gradient as an update to the velocity with which we are going. So basically the gradient will be the acceleration, it will be the change to the velocity. So the velocity at time t plus 1, so at this step, will be a fraction of the velocity so far, and then we're going to add the direction going down the gradient. That's why we are subtracting the gradient, because we want to go down. This is the same thing as we saw before. It's an estimate of the gradient given a random sample of examples, and we use that to change the velocity. And now the update for our parameters will be the learning rate times the velocity of change that we compute here. So this means that if we keep heading in the same direction, with momentum we keep accelerating. So we can compare the two. This is basic stochastic gradient descent. We are sliding down slowly here. But with momentum, since this is always in the same direction, we keep going faster and faster because we keep adding to the previous velocity. So momentum can be a lot more efficient in training the network when we can take advantage of these stretches of the trajectory where we're going basically in the same direction. So in this case, I use the momentum of 0.9. This is the value that the fraction of the previous velocity I'm using, and then changing, accelerating depending on the estimate of the gradient. Another thing that we can use with stochastic gradient descent is a different type of momentum, which is called Nesterov momentum, in which we basically do the same thing, use the previous velocity and use the gradient information to change the velocity, but we are trying to estimate what the gradient would be, not at with the current parameters that we have, but looking ahead at what the gradient would be if we already had taken the step using the previous velocity. So basically, we are looking at the gradient further ahead in our step, and in general, when we are optimizing convex functions, this increases a lot the efficiency of the optimization, because we get better information by looking at approximately where we will be, instead of just looking at where we are, since with momentum we can take fairly large steps. However, this works well when we have an exact computation of the gradient, but doesn't work well with stochastic gradient descent, because even though we're looking ahead, we only have a stochastic estimate of the gradient based on this small sample of examples. So looking ahead or not tends not to make much of a difference. You have this option in stochastic gradient descent in TensorFlow, and you can try, because this in practice can change a bit depending on the problem that you have. But for example, here in this very simple problem, we can see that there is no difference between using momentum, regular momentum, or using Nesterov momentum. So the fact that we are estimating the gradient with some error because we are using a random sample of examples makes Nesterov momentum a lot less efficient. In any case, using momentum is generally a good idea. It makes training a lot faster. So another thing that you can adjust is the mini batch size. Basically, this M here, which determines how many examples we are using to evaluate, to estimate the gradient. There are several things that this can affect. A larger mini batch size means we have a better estimate of the gradient. Since we are estimating the gradient using this random sample, the larger the sample, the better, the more closer this estimate will be to the true gradient of the loss function. However, there is another effect that mini batches have, which is the randomness they give you. If we use larger mini batches, we have less randomness in stochastic gradient descent, and randomness seems to be good at improving generalization. We do not overfit so much, we do not optimize so much the network if we use more randomness. So this, for this, the ideal would be a mini batch size of 1. There you maximize the randomness, but then there is also a trade-off not only for convergence, because if you have too much randomness, then you reduce the ability to converge to the optimum, but also in computation speed, because the main advantage in practice of using these batches is that if we have lots of examples being inserted into the network in one step, the matrix multiplications can be easily parallelized, and so all of these computations can be done in parallel, for example, in the GPU, and this can make training a lot faster. So this is why you often see mini batches, the size of the mini batches being a power of 2. 8, 16, 32, things like that. Because this is generally what is the optimum for GPUs and for this type of parallel computing, where using a power of 2 takes the most advantage of the different cores that you have. So there is basically this trade-off between improving generalization from randomness and improving convergence and accuracy in estimating the gradient by using larger batches. But in practice, often the mini batch size will be limited by memory in real problems where we are dealing with real data that tends to be very large. And so we tend to try to find out how many examples we can put in one go to speed up computation as much as possible. But these are things that you can experiment with and see what optimizes the results in your particular problem that you're solving. So for this example, I'm showing you one dot for each epoch. One epoch is one pass through all the data set. And as you can see in this case, we do not reduce the number of epochs that we need by using a mini batch of 10 or using a mini batch of 1 example. However, this is a bit misleading because this shows you one dot for each epoch and is not taking into account the time it takes to compute over one epoch. So actually mini batch of 10 in time is a lot faster because these operations applied to 10 examples at a time can be parallelized and can be made a lot faster than just doing one by one and then updating the network and repeating. Okay, so let's improve our model. We were using this very simple model with just 2 weights because if I use 3 weights, then all of these plots would become impossible to understand. So this way, using 2 weights, I can represent the 2 weights in these axes and the loss function on the third axis. If I had one more parameter, which would be the bias value there, then I would no longer be able to do those plots. So this very simple pseudo neuron was just to give you an idea of what's going on. Now we're going to start with a real neuron where we have the 2 weights here that multiply by the input, and we have an additional parameter that we can imagine as an additional weight that is always being multiplied by 1. The advantage of this is that we give an additional degree of freedom to our neuron, because if we have only these two weights, regardless of what the weights are, the value that reaches here will always be 0 if both inputs are 0. So there is this one point at 0 where our model is stuck. It cannot deviate from that. So, and you can see here, if you look at the training of this very simple model, the line always passes at this point about here, which corresponds to the inputs being 0, 0. We cannot deviate from this. If we have a bias input, then the line can slide up or down or to whatever side it wants by changing not only the weights that are multiplied by the inputs, but also this additional bias value here. So this is the reason for using these bias values, is that we can have an additional degree of freedom and change the position or the output of our neuron independent of the values of the inputs. Also, we cannot properly separate these data with a single neuron, because this is clearly not linearly separable. So we're going to need more layers. Let's create a network like this, where we have two hidden layers of two neurons each. Note that each neuron has its own bias value. So not only does it have the weights, it has its own bias value here, so that they can all be moved independently of each other and independently of the data by adding those values. We're going to use all sigmoid activations on all these neurons, and we can see what happens during training. This is the original data. This is the representation of the output on the first hidden layer, which starts to transform the data and starts learning how to separate this better. And then what happens on the second hidden layer, which also separates blue and red in a way that simplifies the task for the third neuron, the output neuron in the third layer, to do the classification. And this represents here what we get when we project back the linear classification of the output neuron over these nonlinear transformations, and we get this curved line here. You can also see that this oscillates quite a bit at the end, so I'm going to talk a bit about that, but you see that this model is having trouble converging. When we reach the end of the training, we can see lots of oscillations here, and we are not converging to a better defined solution. Okay, so this gives us some details here that we need to consider when we train the network. One important thing is that we cannot have neurons that are exactly the same, because note that the updates to the neurons, the changes to the parameters of the neurons, are determined by the derivative of the loss function with regards to each particular weight. If the neurons have exactly the same weights and the same bias at the same layer, then for any example they will always have the same derivatives. And this means that they will always be exactly the same, and you'll just have two cloned neurons, or a set of cloned neurons that are always changing in step, and they are not doing anything useful because they are all equal. So we need to break these symmetries. We need to guarantee that the neurons are not equal at the same layers. And so one way of doing this is to assign random values to the weights of the neurons. We can assign the same value to the bias. The bias can start at 0 for all the neurons. That's not very problematic. But as long as they have different weights, they will have different derivatives, and they will diverge depending on what the network needs. But we cannot have neurons with the same weights at the beginning, otherwise the network will not work. Also, in some activation functions, we'll see more a bit on this in future lectures, but if we have activation functions like the sigmoid function, they saturate quickly away from 0. So we should start with random weights close to 0 and close to 0 even when taking into account the inputs and so on. So there are more sophisticated methods for initializing weights. We're going to look at them in future, but the basic idea for today to start implementing some simple networks is to use a random distribution close to 0. For example, a Gaussian distribution, a uniform distribution that is between -1/2 and +1/2, something like that, so that all the neurons start differently and we break this symmetry, and also that they start fairly close to 0 so we don't saturate the activation function, which would cause us to lose information on the derivative, because we'll see this problem next week, but as the activation function saturates, the derivative starts to get closer to 0, and then we have less information about how to change the neurons. So since we initialize the weights at random and we also present the examples at random, we can expect different runs to have different trajectories during training. So if you look at the loss function, for example, you should not expect always to have exactly the same plot, since can vary from run to run. We should also standardize the inputs because there are several reasons to do this. We are starting the weights with the same distribution, so if the inputs are at different scales, this will end up being the same as starting the weights at different scales. In practice, we can avoid that by standardizing the inputs. It's also good to avoid very large values, or combining very large values with small values due to numerical problems, rounding problems, and so on. And shifting everything to 0 and scaling this dimension will improve the shape of the loss function. It avoids having so many narrow values where optimization can get stuck. So standardization, just to a quick reminder, is to bring all your data to a distribution that has a mean of 0 and a standard deviation of 1. To do that, we subtract all our values by the average and then divide everything by the standard deviation of the original values. This will convert something, for example, like this, where one feature is much shorter than the other, into something more like this, where it's more symmetrical, and around here the 0, more centered at 0. We also have this schedule for training. So just to review these terms, one epoch is one full pass through the training data, but then in each epoch we will use many mini batches. So one mini batch will be one subset of the data, one sample of the data that we're going to use to update the network, to estimate the gradient and then apply the gradient information to update the parameters. And we generally need many epochs to train, because we need to pass the data again and again and again. We are adjusting the parameters small steps at a time, so we need to do many passes in order to reach an adequate set of parameters. If we have a very large data set, usually we will need fewer epochs, because passing all the data through the network will pass lots of examples, lots of mini batches through the network, and means lots of updates. If we have a smaller data set, then we need more epochs to train. The basic thing you can think of this as how many mini batches have you passed through the network, so how many times have you updated the weights of the network. The larger the data set, the larger the number of mini batches per epoch that you have. We also should shuffle the data in each epoch. We can see here one possible effect of not shuffling properly, which is you start getting these oscillations due to repetitions in the order of the values that you're giving the network. So to avoid this kind of parameters, we should shuffle the data or randomly select examples in each mini batch. Shuffling is more used because if you shuffle the data and then select non-overlapping mini batches. You guarantee that in each epoch you present each example once and you cover all examples, so you don't repeat examples. But by shuffling, you avoid these kinds of repetitions that may lead to convergence problems and things like that. Another thing that we need to fine-tune often is the learning rate, because if the learning rate is too small, it can take too long to train the network. But if it's large, then we can have difficulty finding the right spot at the end, and so we don't have convergence. We have these kinds of oscillations. But there are more sophisticated ways of doing this. We're going to look at those in the future. For example, starting with a large training rate and then reducing that as we train the network so that we improve convergence at the end. There are lots of tricks like that. There are optimizers that automatically adjust the learning rate and so forth. So, but for now, for these first examples, just bear in mind that you may want to adjust the learning rate and experiment different values to see what works best in each problem. So to sum up this part, we did a bit quick revision of matrix algebra, because matrix multiplication is very important in training neural networks. We saw automatic differentiation. Remember, this is not the same as numerical differentiation. We are not trying to estimate the gradients by small steps. We are actually using the analytical expressions for the derivatives. But what TensorFlow does is use these derivatives for each basic operation in parallel with the actual operation. So basically there is one first pass where it computes all the intermediate results, and then it applies, going backwards, applies all the gradient expressions in order to compute the derivative of the function with respect to any variables we want to update. And we saw still here a bit in abstract how we can use these layers, nonlinear transformations, and train the multi-layer feed-forward network. So I recommend that you take a look at these chapters for the algebra, calculus, and the optimization part. We are the level of detail that you need for grading in this course is the level I give you in the slides and the lecture notes, but it's a good idea to take a look here and also in the tutorial that you have later on, so that it helps you understand the basic concepts. Let's take a small break and we continue at 10 with the implementation in TensorFlow. See you soon.